Okay, Module 4, Video B, Building Decision Trees. So to start off here, we need to import some packages. As you can see, we'll be using pandas, NumPy, and then a bunch of different functions from the Sklearn library. Sklearn or Sklearn is a module for really meant for making data science models. Specifically, today we'll be doing a decision tree, but they have models for regression, for classification, gradient descent, all sorts of things. So we'll import those. As mentioned before, we'll be using the Boston housing data set. Here's an overview of what all those variables are. And then the first thing we need to do after importing our data, which we'll do in this line right here, is we need to split it into a testing and a training data set. This is something that we didn't do in the linear regression model, but that we will often do in any sort of kind of more complex model, especially if you get into any sort of other like machine learning or neural networks, is it's important to train your model on one set of the data but test it on a separate section. And that is because more complex non-linear models such as decision trees, they have a tendency to do what we call overfitting. And that is where they learn the data you train them on so well that it actually becomes a hindrance when you get to predicting new data. So instead of just learning general trends about the data, the model will start memorizing specific data points. And so you might get super good accuracy on the trained data, but then when you run the model on the test data, which is data the model hasn't been trained on, your accuracy won't be very good. So that's why one of the first things we're going to do here is we'll define our X, which that's just going to be the data set with medv, our responsive variable dropped. Then Y, of course, is medv. And then we'll run this function right here. And what that is doing is it's splitting out our data set so that we'll have an X train data set, an X test data set, a Y train, and a Y test data set. And that is all done using this train test split function, which is one of the functions we imported from sklearn. So we can see that we pass it in X, Y, we give it the test size, which is 0.2, so that means it's going to reserve 20% of the data for testing. And then I'm also doing something right here. I'm specifying the random state. So in Python, whenever you use a function that involves randomization, you'll often have the option to select a random state. If I didn't select a random state, then every time I ran this bit of code, it would split the data differently. It would do a new random split and I would have a new test and a new trained data set. However, for consistency and so that if you're running the code, it will be the same as when I'm running the code, I'm going to set the random state. And you can really set the random state to anything, just any integer. I chose 42. But this means now that the random state is set, the output will be the same every time we run this code, which I'm going to go ahead and do right now. Okay, so we have our test training set and our training set and our test set. So let's go ahead and fit a tree. As mentioned, we're using the scikit-learn. And then this is how we're going to initialize the model. So we initialize the model using this decision tree regressor. That was one of the functions we imported at the first. And for this very first one, I'm not going to really specify any parameters. I've specified the random state, but that's all. We'll see later on there's a lot of arguments that we can add here that are going to control how big our tree gets. Right now, I'm not going to put any arguments in, and then we'll fit our model using model.fit. You can see that we fit it on the X train and the Y train data. And then I am going to make predictions. We'll store those in ypred. And then also we'll print out the mean squared error. So let's do that. So that fits our model, and it prints out that we have a testing mean squared error of 22. Now, if you watched the linear regression model, you might remember that at the end of our linear regression fitting, we had a mean squared error of, I believe, 19. So this isn't doing super good. And let's look at why it's maybe not doing well. So using this right here, we're going to export the data from the tree, and we're going to graph it using GraphViz. And let's run that, and we'll look at the tree that it has made us. So I'm going to have to scroll way, 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 way down. And then let's scroll over to just give an idea of how big this tree is. So we're scrolling along the bottom. And here, let's start, because I've kind of even lost it. It's hard to actually, can I zoom out, give you an idea of just how massive this tree is. And this is just the bottom half of the tree. Let's scroll up a bit, and then we'll scroll over and see if we can actually find the top of the tree somewhere in here. There. Oh, nope, still not the top of the tree. This guy maybe. It looks like that is our root node. So as you can see, this has fit an absolutely massive tree. I'll start zooming back in so we can see our other text. So when we run this, where did it go? This decision tree regressor, if we do not specify any of the other parameters, it will keep building the tree. It will keep splitting and splitting and splitting and splitting until it has made a separate node for every single data point. So if I scroll back down here, you can see that each end node, each leaf node, only contains one sample. I don't know why it glitched like that, but yeah, so each leaf node only contains one sample. Each leaf node says we have a squared error of 0, and the value it's predicting is just exactly what the value of that data point is. So this has just split and split and split and split until it has a separate leaf node for every single data point that we gave it. So this is the definition of overfit. This is completely overfit. It's massive. It's not very useful to us if we're trying to interpret what's going on. And as we saw before, it also doesn't generalize very well to new data. So this is not what we want. And in the next video, we'll talk about how we can set the hyperparameters to prune our tree and make a more useful and understandable decision tree.